Hello, everyone. Today I'm going to teach Chapter 8, Section 8.1 and 8.2. So first I'm going to teach Section 8.1, and then another video I'm going to teach Section 8.2. So the Chapter 8 is about the sampling distributions. In section 8.1, distribution of a sample mean, the learning objectives is number one, we describe the distribution of a sample mean, normal population. So we describe the distribution of a sample mean for the normal population. And then objective two, we describe the distribution of a sample mean with the non-normal population. So we describe the distribution of a sample mean with the normal population, and then we describe the distribution of a sample mean of a non-normal population. Okay. Statistics such as X bar are random variables since their value varies from sample to sample. And again, guys, what was the statistics? The definition of a statistics. So it's the science of collecting, organizing, summarizing, analyzing the data to draw a conclusion or answer a question. So statistics such as X bar are random variables since their value varies from sample to sample. As such, they have probability distributions associated with them. In this chapter, we focus on the shape, center, and a spread of statistics such as X bar. Again, guys, statistics is the science of collecting, organizing, summarizing, analyzing the data to draw the conclusion or answer a question, so such as X bar. So let's move on. Okay, so the sampling distribution of a statistic. This is a statistic. And again, guys, what was the statistic? Is a numerical summary based on a sample. So a statistic is a numerical summary based on a sample. So the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. So again, the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. And again, guys, what was the statistic? Is a numerical summary based on a sample. The sampling distribution of a sample mean X bar is the probability distribution of all possible values of the random variable X bar computed from a sample of size n from a population with the mean mu and standard deviation sigma. So again, the sampling distribution of a sample mean X bar is the probability distribution of all possible values of the random variable X bar computed from a sample of size n from a population with the mean mu and a standard deviation sigma. Okay, how we do that? Step one, we obtain a simple random sample of size n. So step one, we obtain a simple random sample of size n. Step 2, we compute the sample mean. So we compute the sample mean. Step 3, assuming that we are sampling from a finite population, repeat steps 1 and 2 until all distinct simple random samples of size n have been obtained. So assuming that we are sampling from a finite population, repeat steps 1 and 2 until all distinct simple random samples of size n have been obtained. So again, guys, don't worry. I'm going to show you guys an example so you guys understand these steps. Okay, let's do it. Example 1, sampling distribution of a sample mean normal population. Again, guys, this is for normal population. The weights of pennies minted after 1982, so 1982, are approximately normally distributed. So approximately normally distributed with the mean 2.46 grams and a standard deviation of 0.02 grams. So again, guys, the weights of the pennies minted after 1982 are approximately normally distributed. The mean is 2.46 grams. That's the mean of the population. And the standard deviation of a population is 0.02 grams. What I'm asking for is approximate the sampling distribution of a sample mean by obtaining 200 simple random samples of size n equal to 5 from this population. So that means I'm going to take a simple random sample of size n equal 5. Then I'm taking another simple random sample of size n equal 5. And I repeat this until I obtain 200 simple random samples. So I have a distinct, so each one is unique. So they are distinct, okay? So let's do it. Okay, the first one. So let's do the first one. So the data on the following slide represent the sample means for the 200 simple random samples of size n equal 5, but this is the first one that I show you guys in this slide. For example, the first sample of n equal 5, so again, I'm going to take a simple random sample of size n equal 5 for the first time. So I'm going to take 2.433, 2.466, 2.423, 2.442, 2.456. So I'm going to weight it each. I choose 5, and then I weight it, and I record the weight for each one. So the first one, 2.433, 2.466, 2.423, 2.442, and 2.456. And then I'm going to find the X bar. So I'm going to add these up divided by 5. So the X bar is equal to 2.444 for this sample. Then I'm going to repeat this. I'm going to repeat this for 200 simple random sample. And again, guys, each one of these is going to be unique. So the next slide. You see that these are the sample means for the sample of size n equal 5. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 3, 6, yeah, 10 times 10. So this is for the 100 simple random sample. And then the next slide, and you see that each time that I take a simple random sample, I find the X bar for each one of them. So this is for the 100. And then this is for another one, another 100. So the total is 200. So we take a simple random sample of size n equal 5 for 200 cases. And again, each case is unique. So they are distinct. And then Now the mean of the 200 sample mean is 2.46. This is the same. So again, guys, if I put all these in the computer and find the mean of it, the mean is 2.46. And look, this is the same as the mean of the population. Remember, when I show you guys the problem at the first, the mean of the population was 2.46. And now when we take a 200 sample and find the mean of it, so the mean is 2.46 and it's the same as the mean of the population. Keep that in mind. The standard deviation of a sample mean is going to be 0.0086. This is smaller than the standard deviation of the population. So this is smaller than the standard deviation of the population. So what's my conclusion here so far? The mean of the sample is the same as the mean of the population, and the standard deviation of a sample is smaller than the standard deviation of the population. So the next slide shows the histogram of a sample mean. Okay, guys, this is a histogram of a 200 sample mean when n is equal to 5. So if you guys look at it, you see it's not really symmetric or looks like or approximately normal, okay? So see what happened. Okay, guys, what role does n, the size, what role does n, the sample size, play in the standard deviation of the distribution of a sample mean? So what role does n, the sample size, play in the standard deviation of the distribution of a sample mean? Here we go. As the size of the sample increases, the standard deviation of a distribution of a sample mean decreases. So as the size of the sample increases, the standard deviation of a distribution of a sample mean decreases, okay? So now see if it's true. Okay, example 2. The impact of the sample size on sampling variability. So approximate the sampling distribution of a sample mean by obtaining 200 simple random sample of size n equal to 20. Remember, last time n was equal to 5. Now we increase 5 now to 20. Now see what happened to the standard deviation and the mean. Okay, guys. So again, guys, let me read the problem. Approximate the sampling distribution of a sample mean by obtaining 200 simple random sample of size n equal 20 from the population of weights of pennies minted after 1982. Again, guys, the mean of the population is 2.46, and the standard deviation of a population sigma is equal to 0.02. So now I'm going to, again, the things that happen here, I increase size n equal 5 to n equal to 20. Now see what happened. Okay, guys, if you look at the histogram, see what happened. The mean of the 200 sample mean for n equal 20 is 2.46. So again, guys, you see it still is the same as the mean of the population, but the standard deviation is now it's 0.0045. And again, guys, we use technology to find the standard deviation, and the standard deviation is now 0.0045, even is smaller than when n is equal to 5, because when n equal to 5, the standard deviation was 0.0086. So now n is equal to 20, the standard deviation decrease more, so now it's 0.0045. So again, guys, as expected, there is less variability in the distribution of a sample mean with n equal 20 than n equal 5. So yes, that was true. So as n, the sample size n increasing, the standard deviation is going to be decreasing. So now let's move on. Okay, guys, here we go. The mean and standard deviation of a sampling distribution of X bar. Suppose that a simple random sample of size n is drawn from a large population with the mean mu and a standard deviation sigma. So again, suppose that a simple random sample of size n is drawn from a large population with the mean mu and a standard deviation sigma. The sampling distribution of X bar will have the mean. Okay, guys, as we concluded based on what I said from the beginning of this section, the mean of the X bar, the mean of the sample, is the same as the mean of population. So the mean of the X bar, the mean of the sampling distribution, is the same as the mean of the population. And then the standard deviation, the sigma X bar, is equal to the standard deviation of the population sigma is divided by a square root of sample size n. So again, guys, the mean of the X bar, the mean of the sample, is the same as the mean of the population. And then the standard deviation of the X bar, the sample, is the same as the standard deviation of a population divided by the square root of sample size n. The standard deviation of a sampling distribution of X bar is called the standard error of the mean and is denoted, as I showed to you guys, that is sigma X bar. Okay, so okay, now the shape of the sampling distribution of X bar if X is normal. So obviously, if a random variable X is normally distributed, the sampling distribution of a sample mean X bar is also normally distributed. So if a random variable X is normally distributed, the sampling distribution of a sample mean X bar is normally distributed. Okay. So now let's do a problem together, okay? So the weight of pennies minted after 1982 are approximately normally distributed. So again, guys, when it says approximately normally distributed, that means this is a bell-shaped, so and then is a normally distributed. The mean of the population is 2.46 grams, and a standard deviation of population is 0.02 grams. So again, guys, the mean of the population is 2.46 grams, and the standard deviation of a population is 0.02 grams. Now, what is the question? What is the probability that in a simple random sample of 10 pennies minted after 1982, so that means n is equal to 10, we obtain a sample mean of at least 2.465 grams. So when I said at least, again, guys, that means my minimum. So for example, if I said at least 5, that means my minimum could be 5 and then greater than 5, correct? So at least 5, that means the minimum could be 5, and then I'm going to look for 5 and greater than that, correct? So it's here, it says at least 2.465. That means I'm looking for area to the right. So let me, okay guys, first of all, the mean of X bar is the same as the mean of the population. So this is equal to 2.46. Okay. And then the standard deviation of a sample, again, guys, as I mentioned in the previous slide, was the standard deviation of a population divided by a square root of n. So again, guys, the standard deviation of the population was 0.02 over a square root of n is 10. Okay. So again, guys, I'm looking for area to the right. Why? I know that because it says at least 2.465 grams. So if I said less than 2.465 grams, that means I'm looking for area to the left. But because it says at least, that means we're looking for greater than 2.465 and greater than that. That means I'm looking for area to the right. Okay. But again, guys, first, I have to find the z-score. And again, guys, the formula to find the z-score is going to be z equal to x bar minus the mean of x bar divided by the standard deviation of a sample, that is a standard deviation of a population over a square root of n. And again, guys, make sure when you do this on your calculator, put numerator in parentheses, divided denominator, again, put the denominator in parentheses. So let's do it. So it's going to be equal to, so again, guys, x bar in this case is 2.465 minus the mean of the sample. Again, guys, it was the same as the mean of the population. So it's going to be 2.46 all over, and then again put it in parentheses. Again, the standard deviation of a population is 0.02 divided by a square root of n is 10. Okay, guys, if when you punch this in your calculator, so, and again, guys, the z-score is always, you should round it to the 2 decimal places. So it's going to be 0.79. So 0.79. So again, guys, if you punch this in your calculator, you should, and round it to the 2 decimal places, you should get the z-score of 0.79. And again, guys, now this is a positive z-score. So we look at the A-12 in your, again, in your electronic version of your book. A-12 is going to be positive z-score. But again, guys, all those area in A-11 and A-12 is all area to the left. But in this case, I'm looking for area to the right. First, I'm going to find the area to the left, and then 1 minus that show me the area to the right. So the area to the right the area to right is equal to 1 minus, again guys, if you look at the z-score, 0.79 in the H-12, the area to the left is 0.7852, and 1 minus that gives me the area to the right. So again guys, the area to the left 0.7852, and 1 minus that give me the area to the right, that is 0.2148. So what is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams? So the area to the right, the probability is 0.2148. Okay, so let me erase this. Okay, so now let's go over the answer together. So again, guys, here. So again, X bar is normally distributed. The mean of X bar is the same as the mean of the population, 2.46. And then the sigma of a sample is the sigma, the standard deviation of a population is divided by the square root of the sample size 10. And again, guys, here we can punch in the formula for the z-score, X bar minus the mean of the X bar divided by the standard deviation of a population divided by a square root of n. And as you see that, we get 0.79. And then I'm looking for area to the right. So first I'll find the area to the left, and 1 minus that give me the area to the right. So the answer is 0.2148. So hopefully you guys completely understand this part. Okay, guys, this is the first example. So now let's move on. So this is for normally distributed. So it's a normal population. So now let's go to non-normal. So the following table and histogram give the probability distribution for rolling a fair dice. So again, guys, face on the dice, we have a 1, 2, 3, 4, 5, 6. And again, guys, if I ask you what's the probability for each face, actually is going to be, all is going to be 1 out of 6. So they have a same probability. So the relative frequency for each face is going to be 0.1667. And again, guys, if you look at the histogram, you see that it's all the same, okay? So if I find the mean is going to be 3.5, the mean of the population, and the standard deviation of a population is 1.708. Note that the population distribution is not normal. Obviously, they are not normal because they are all the same, okay? So now the question is, okay, what happened in this case? Okay. Estimate the sampling distribution of an X bar by obtaining 200 simple random sample of size n equal to 4. So now, they ask me estimate the sampling distribution of X bar by obtaining 200 simple random sample of size n equal 4, n equal 4, and calculating the sample mean for each of 200 samples, and repeat this process for n equal 10 and then 30. What we are doing, we increase the sample size. So first we do this process when n equal 4, then we do this process for n equal 10, and then we do this process for n equal to 30. Histograms of the sampling distribution of a sample mean for each sample size are given on the next slide. So see what happened when we increase the sample size. So let's do it. Okay, guys, this is the histogram when sample size n equal to 4. So you see that obviously is not symmetric, okay? So because the tail is not the same, and if you guys see, is not the symmetric, so they are not the same size in the same format in the both side, okay? So it's obviously is not symmetric, okay? So now we increase n equal 4 to n equal to 10. So now you see it still is not that really symmetric. It gets better, but it's not really symmetric still, okay? Now see what happened when we increase it to n equal, now do you guys notice? Now this is approximately normal. You see that if I take it in half, the half is the mirror of the other one, approximately. So you see that now this is approximately normal. Okay, what's my conclusion? Key points from example 4. The mean of the sampling distribution is equal to the mean of the parent population, and the standard deviation of the sampling distribution of a sample mean is a standard deviation of a population divided by the square root of sample size, regardless of the sample size. So let's go back one more time. So again, guys, you see that here, again, guys, n is equal 4. You see that is not symmetric, okay? And then n equal 10, it gets better, but it's not really symmetric. And then, but n equal 30, you see that now it's symmetric, approximately symmetric, so it's approximately normal. So the key points from example 4, the mean of the sampling distribution is equal to the mean of the parent population. Again, guys, that's the same thing. The mean of the X bar is the same as the mean of the population. And again, the standard deviation of a sample is the standard deviation of a population divided by the square root of n, regardless of the sample size. The shape of the distribution of a sample mean becomes approximately normal as the sample size n increases, regardless of the shape of the underlying population. So again, guys, the shape of the distribution of a sample mean becomes approximately normal as the sample size n increases, regardless of the shape of the underlying population. So, and that is called the central limit theorem. So the central limit theorem, regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size n increases. So the central limit theorem, again, guys, this is really important. Make sure learn this theorem, the central limit theorem, regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal when as the sample size n increases, as I showed to you guys on previous slides. Okay, guys, now let's do the again a problem. So example 5, we are going to use the central limit theorem. And again, guys, this is for non-normal population. So for the non-normal population, we are going to using the central limit theorem to do this example. Suppose that the mean time for an oil change at the 10 minutes oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. Again, guys, 11.4 is the mean of the population and the standard deviation of a population is 3.2. So again, guys, the mean of X bar is the same as the mean of the population, and that is 11.4. And then the standard deviation of a sample is equal to a standard deviation of a population divided by the square root of sample size. So in this case, the standard deviation of a population is 3.2 divided by the square root of n is 35. So again, guys, part A, it says if a random sample of n equal 35, that I mentioned that before, all change is selected, describe the sampling distribution of a sample mean. So again, guys, in the homework, when they ask you describe the sampling distribution, that means that you should tell me that the mean of the sample bar is the same as the mean of the population, so it is 11.4. And then the standard deviation of a sample is the same as the standard deviation of a population divided by the square root of sample size, so it's going to be 3.2 over a square root of 35. And again, guys, if you punch this in your calculator, it's going to be 0.5409. So now let's go to the part B, okay? So let me again erase this. So now let's see what the B says. Okay, guys, part B, it says if a random sample of n equal 35 all changes is selected, what is the probability that the mean all change time is less than 11 minutes? Again, guys, when I said less than, that means area to left. So in this case, I'm good to go because this is the area to the left. So, and then again, guys, A-11 and A-2, all the A-12, all those area is area to the left. So I'm good to go. So I'm looking for less than 11 minutes. So I'm going to find the area to the left. So again, guys, the z-score, the formula for the z-score is going to be X bar minus the mean of X bar over, again, a standard deviation of a population divided by a square root of sample size. Again, guys, make sure put the numerator and denominator in parentheses. So now I'm going to say, okay, this is 11, because again, guys, less than 11 minutes. So X bar is 11 minus the mean of the sample bar, again, is the same as the mean of the population. So it is 11.4 from part A divided by a standard deviation of a population is 3.2. Again, that's from part A. And then a square root of sample size, that is a square root of 35, okay? So again, guys, if I punch this in my calculator, again, numerator in parentheses, denominator in parentheses, and then round it to the 2 decimal places, you should get negative 0.74. So the z-score is negative 0.74. And again, guys, because it says less than 11 minutes, I'm going to find the area to the left. So I look at, since the z-score is negative, I should look at the A-11 and then look at the area to the left. So the area to the left is 0.2296. Again, guys, I don't like the way that the PowerPoint says rounded to the 2 decimal places. So make sure, guys, in the exam later on, when we have an exam for chapter 8, make sure write it completely with the 4 digits. So it's going to be 0.2296. So area to the left, because it says it's less than 11 minutes, so area to the left is 0.2296, and that's it. So again, guys, let me erase this. Okay, guys, that's it. So this is 8.1. So I'm going to finish this recording, and then I'm going to start 8.2 in another video. So let me see.